Today we are going to talk about the second half of Chapter 2. In the first half of Chapter 2, we talked about what happens when we multiply and divide and how we determine how many significant figures our final answer should have. In this section, we are going to talk about what happens when you add or subtract numbers. So when we multiply or divide numbers, we said that our answer should have the same number of significant figures as the fewest. In adding and subtracting, your final answer is written so that it has the same number of decimal places as the measurement with the fewest decimal places. So in this case, it hasn't anything to do with how many significant figures you have, rather how many decimal places you have. In example 8, it says if you add 2.012 plus 61.09 plus 3.0. If you type those numbers into your calculator, you will get 66.102. Sorry, my stylus isn't working here at the moment. 66.012. The first number that we typed in, 2.012, has 3 decimal places. The second number, 61.09, has 2 decimal places. The final number that we added, 3.0, has 1 decimal place. Therefore, our answer should have 1 decimal place. If we draw our line here, the number immediately following the line is a 1. Therefore, we round down. So our final answer is 66.0. Let's look at example 9. It says subtract the following measured numbers, 65.09 minus 3.0. Typing in this into your calculator, you should get 62.09 as your answer. The first number, 65.09, has 2 decimal places. The second number, 3.0, has 1 decimal place. Therefore, our answer should have 1 decimal place. Drawing our line, we see that the number immediately following the line is a 9. 9 is larger than 5. So our final answer should be 62.1. Let's look at another example. 82.409 plus 22.0. Typing this in our calculator, we get 104.409. Looking at our first number, we have 3 decimal places. Our second number has 1 decimal place. Therefore, our answer should have 1 decimal place. Drawing our line, the number immediately following is a 0. So our answer should be 104. Oops, I'm sorry. Yes, 104.4. Okay. Equalities. Equalities use 2 different units to describe the exact same measured amount. They are written for relationships between units of the metric system, US units, or between metric and US units. For example, we said previously that 1,000 millimeters equals 1 meter. We can also say that 16 ounces equals 1 pound. Or between the 2 different systems, metric and American, we can say that 2.20 pounds equals 1 kilogram. So let's try it. Using an equality, we can write a conversion factor. The equality, minutes to hours, is that 60 minutes equals 1 hour. Right? The conversion factors that we can write from this are 60 minutes divided by 1 hour, or 1 hour over 60 minutes. Okay. We can also do this for meters to centimeters. As we said in the previous lecture, 100 centimeters equals 1 meter. Conversion factors, we could write it this way, 1 meter over 100 centimeters, or 100 centimeters over 1 meter. The numbers in an equality between 2 metric units or 2 US units are an exact number. Remember, when we are going between the same system, it's always exact. The reason for this is that they are considered a definition. A definition is exact and is not used to determine significant figures. Most equalities between metric and US units contain one number that is obtained by measurement and counts towards the significant figures. The other number is considered exact. There is one exception to this rule. The exception is between inches and centimeters. The equality 1 inch equals 2.54 centimeters has been defined as an exact relationship. Therefore, the 2.54 is an exact number and does not count towards your significant figures. So if we were to write our metric conversion factors, we would say 2.54 centimeters over 1 inch, or 1 inch over 2.54 centimeters. Both of these are proper conversion factors for the relationship. One is just the inverse of the other. We can write metric system to US system conversion factors, metric to metric, or US to US. Let's write conversion factors from the equality for each of the following: liters and milliliters. We said in the previous lecture that there are 1,000 milliliters in 1 liter. Uh-oh. Okay. The conversion factor for this is 1,000 milliliters divided by 1 liter, or 1 liter divided by 1,000 milliliters. Both are correct. Both are used in different situations. So let's erase this. All right, how about meters and inches? We said that there are 2.54 centimeters in 1 inch. Okay. Therefore, there are 0.02. Remember that there are 100 centimeters in a meter. There are 0.0254 meters in 1 inch. And vice versa. 1 inch has 0.0254 meters. Yeah. Now let's erase this so we have room to deal with the next problem. The next problem says between meters and kilometers. We said in the previous lesson that this is a conversion that you need to know, right? We need to know how many meters are in a kilometer. There are, if you recall, 1,000 meters in 1 kilometer. And we can write conversion factors for this. This is the equality. The conversion factor is written as a fraction. 1,000 meters over 1 kilometer, or 1 kilometer over 1,000 meters. Again, let's just erase this real quick so we have room to deal with the next example. Okay. The next example says equalities stated within dosage problems for medication can also be written as conversion factors. Keflex, formal name cephalexin, is an antibiotic used for respiratory and ear infections. It is available in 250 milligram capsules. Therefore, one capsule has 250 milligrams, or there are 250 milligrams in 1 capsule. A percentage can also be written as a conversion factor by choosing a unit and expressing the relationship as parts of this unit to 100 parts of the whole. For example, a person might have 18% body fat by mass. Therefore, they have 18 grams of fat for every 100 grams of body mass. Right? Or you could say 18 kilograms for every 100 kilograms of body fat. You could also say 18 pounds of fat for every 100 pounds of body weight. Again, you choose the unit and then you express that amount as 100 parts of the whole. Okay. Example 13. Write the equality and its corresponding conversion factors. Identify each number as exact or give it significant figures in the following statement. Salmon contains 1.9% omega fatty 3 acids. Therefore, there are 1.9 grams of omega-3 fatty acids in every 100 grams of salmon. Okay? This is the measured number. This is the exact number. Okay? The corresponding conversion factors would be 1.9 grams of omega-3 fatty acids per 100 grams of salmon. Or, for every 100 grams of salmon, you have 1.9 grams of omega-3 fatty acids. Example 14. Write the equality and conversion factor for each of the following: meters and centimeters. This is very similar to the previous example. There are 100 centimeters in 1 meter. So the equality is 100 centimeters equals 1 meter. The conversion factor is 1 meter over 100 centimeters, or 100 centimeters over 1 meter. Jewelry that contains 18% gold is just like the salmon example, right? That means that there are 18 grams of gold for every 100 grams of jewelry. So the equality factor is 18 grams of gold for every 100 grams of jewelry. The conversion factor for this is 18 grams of gold per 100 grams of jewelry. And vice versa. 100 grams of jewelry contains 18 grams of gold. Let's look at the final example. The final example says that 1 gallon of gas is $3.40. We do this in our everyday lives, right? 1 gallon equals $3.40. The conversion factor is $3.40 per 1 gallon, or 1 gallon costs $3.40. Example 15. A person weighs 164 pounds. What is their body mass in kilograms? So step 1 says to state the equalities and conversion factors. We saw on our previous page, if we go back and look, that, let's see if I can find it here. There it is, 2.20 pounds equals 1 kilogram. So let's go back here to our example. We know that 2.2 pounds equals 1 kilogram. We wish to get from pounds to kilograms. So let's set up the problem and cancel our units. 164 pounds is what we're starting with. We wish to write a conversion factor that will enable us to cancel our units. Therefore, we want the pounds on the bottom. 2.2 pounds per 1 kilogram. This enables our pounds to cancel, leaving us with kilograms. 164 divided by 2.2 gives us, in our calculator, an answer of 74.54545455. Right? This is, of course, way too many numbers. So let's look at our significant figures. Okay, 2.2, right? Remember we said that going between systems, one contains significant figures, the other is exact. In this case, the 2.2 is the number with the significant figures. There are 2. And the 1 kilogram is the exact number. So there are 2 significant figures in this number and 3 in our initial number. We were performing a division. Therefore, we want the answer with the fewest number of significant figures, which would be 2. There is our dividing line. The number after it is a 5. So our final answer, when rounded correctly, is 75 kilograms. Example 16. A rattlesnake is 2.44 meters long. How many centimeters long is the snake? From the previous lecture, you should remember that centimeters is a unit. You should know there are 100 centimeters in 1 meter. All right, so our conversion factors are 100 centimeters divided by 1 meter, or 1 meter divided by 100 centimeters. Our initial unit is 2.44 meters. We wish to set up a conversion factor that will enable us to get rid of our meters and find centimeters. So therefore we want the meters on the bottom. 1 meter is equal to 100 centimeters. Our meters cancel, and we should have an answer in centimeters. Typing this in our calculator gives us 24400, or 24,400. Now we need to make sure that this answer has the correct number of significant figures. There are 3 significant figures in our initial number. In the second number, where we have the equality, we are going between the same system of measurement, centimeters and meters. Therefore, these numbers do not count towards our significant figures. So our answer should have 3 significant figures. Our answer should have 3 significant figures. Since there is no decimal point, our answer currently contains 3 significant figures, and we don't need to do anything. So, when you're problem solving, 2 or more conversion factors might be needed to complete the change of units. So far, we've been able to get there using just 1. But what do we do if we need 2 or more conversion factors? So, for example, a doctor's order prescribes a dosage of 0.150 milligrams of Synthroid. If the tablets contain 75 micrograms of Synthroid, how many tablets are required to provide the prescribed medication? The first thing that we need to know is how many micrograms are in a gram. If we were to look this up, we would see that there are 1 million micrograms in a gram. Okay? Then we need to get from grams to milligrams. There are, of course, 1,000 milligrams in 1 gram. Okay? So let's set up our problem to cancel units and calculate the answer. We need 0.150 milligrams. We have 75 micrograms in 1 tablet. So 0.150 milligrams is what we would like to get to. 1 tablet contains 75 micrograms. 1 tablet contains 75 micrograms. So we need to convert our micrograms into milligrams in order for this to be useful. So we just said that there are 1 million micrograms in 1 gram. So if you take your 75 and divide it by 1 million, okay, and then taking that answer, right, this is our answer now in grams, we need to get from grams to milligrams, so then we would multiply by 1,000. We would have 0.075 milligrams in 1 tablet. Okay? 0.075 milligrams in 1 tablet. So how many tablets are we going to give our patient? 0.150 divided by 0.075 tells us that we are going to give our patient 2 tablets. Now, do we need to look at significant figures here? Well, tablets are something that you would count out, right? So in this case, we do not need to look at significant figures since we are dealing with something that is an exact amount. Okay? You give 2 tablets, not 2.1 or 1.9. Okay, how many minutes are in 1.4 days? Well, if we are starting with 1.4 days, do you know how many minutes there are in 1 day? I don't happen to know that off the top of my head, but I do know that 1 day has 24 hours. I also know that 1 hour has 60 minutes. This is another example of a two-step calculation. I don't know how many minutes are in a day, but I know how many hours are in a day, and I know how many minutes are in an hour. So my days cancel, my hours cancel, and I am left with minutes. So 1.4 times 24 times 60 in my calculator tells me that there are 2016 minutes in one day. I'm sorry, in 1.4 days. Significant figures. Do we count the significant figures between hours and days or between minutes and hours? Again, those are between the same system of measurement. So we don't have to look at those significant figures. So our answer should have the same number as our starting, which is 2, right? If we draw our line and we look here, we would round this, right? That is a 1, so we would round this to 2,000. However, how many significant figures does 2,000 have? It only has 1, right? So in order to get this to 2 significant figures, we have to put this in scientific notation. 2.0 times 10 to the third, right? 2.0 times 10 to the third minutes. This gives us an answer with 2 significant figures. Example 19. If your pace on a treadmill is 65 meters per minute, how many minutes will it take you to walk a distance of 7.5 kilometers? So we want to know how long to walk 7.5 kilometers. Okay, this is a conversion factor you would have to look up. How many kilometers per mile? If you were to look this up, you would see that there are 1.61 kilometers in 1 mile. Okay, 1.61 kilometers in 1 mile. So let's figure out how to get from kilometers to miles. Or 1.61 kilometers in 1 mile. Okay. Now, your pace is 65 meters per minute, right? We need to get from kilometers to meters, right? From kilometers to meters. Oh dear. We've hit a dead end, haven't we? Well, let's retry this problem, perhaps going a different way. Sometimes this happens, right? We're in miles. We needed to be in meters, right? Because our pace is in meters per minute. So let's try this a different way. Instead of converting to kilometers, from kilometers to miles, let's go from kilometers to meters. This happens sometimes in chemistry, right? And it is best to be able to stop, restart, and figure out a new way. So, 7.5 kilometers. Initially, we went to miles, right? But our pace on the treadmill is meters per minute. So, instead of going to miles, let's go to meters. There are 1,000 meters in 1 kilometer. 1,000 meters in 1 kilometer. Okay? Now, our pace is 65 meters per minute, and we want to get to minutes. So 65 meters per 1 minute leaves us with an answer in minutes, right, with our meters canceling. So 7.5 times 1,000 divided by 65 gives us an answer in our calculator of 115.3846154. This is clearly more significant figures than we need. Our initial had 2. The 1,000 meters in 1 kilometer is within the same system of measurement, so this is exact. Our minutes and 65 meters, right? The 65 meters per minute, this is significant, this is exact. So we have 2 significant figures and 2 significant figures. Our answer should have 2. Here's our dividing line. Let us round, and you get 120 minutes. It will take you 120 minutes, or roughly 2 hours, to walk a distance of 7.5 kilometers, giving that speed. One measure of toxicity, which is important in medicine, is the LD50, or the lethal dose, which is the concentration of a substance that causes death in 50% of test animals. Dosages are typically measured in milligrams per kilogram of body mass, or micrograms per kilogram of body mass, just like we saw with the percentages. And then finally, another type of important measurement that you may see is density. Density compares the mass of an object to its volume. Okay? Density equals mass of a substance divided by volume of a substance. So a question asks, what is the density in grams per centimeter cubed of a 48-gram sample of metal if the level of water in a graduated cylinder rises from 25 milliliters to 35 milliliters after the metal is added? Well, this comes from the type of problem where measuring volume isn't always easy. Right? If you have a cube, you can measure the three sides, multiply all three sides, and get it in meters cubed or centimeters cubed. But sometimes you have an unevenly shaped object. When that happens, if you take your unevenly shaped object and you put it in a graduated cylinder with water in it, when you do this, put your metal in, the water level will rise. The volume of your irregularly shaped object is the difference between the initial volume and the final. So density equals mass over volume. You are given the mass, it is 48 grams. Okay. And the volume, again, is the final minus the initial. So the volume is 33.0 minus 25.0. So here we have two different things going on, right? We have a subtraction on the bottom and then a division. So for significant figures, if you say 33.0 minus 25.0, your answer in your calculator is 8. However, since we are going addition and subtraction here, we need the least number of decimal places. You have one decimal place in each of these, so your answer rather than 8 should be 8.0. So you have 48.0 divided by 8.0. If you type this in your calculator, 48.0 divided by 8.0 gives you the number 6. However, you have 3 significant figures on the top and 2 significant figures on the bottom. Therefore, your answer should have 2 significant figures. 6.0 grams. Now, your answer is in grams per milliliter. However, you might remember from Chapter 2, Part 1, that 1 centimeter cubed is equal to 1 milliliter. Therefore, you can report this as 6.0 grams per centimeter cubed. Okay. Example 21. John took 2 teaspoons of cough syrup. If the syrup had a density of 1.20 grams per milliliter, and there is 5 milliliter in 1 teaspoon, what was the mass in grams of the cough syrup he took? Well, we said that density equals mass over volume, right? We are given the density, and we are given 2 teaspoons, which is not yet a volume. However, we are also told that there are 5 milliliters in 1 teaspoon. Therefore, we can get a volume in milliliters from that information. If there are 5 milliliters in 1 teaspoon, how many milliliters are in 2 teaspoons? So the density of the cough syrup is 1.20 grams per milliliter equals the mass divided by the volume. Well, again, if there are 5 milliliters in 1 teaspoon, there must be 10 milliliters in 2 teaspoons. Right? Multiplying both sides by our 10 milliliters to get our mass, we have 1.20 times 10.0 for a total in our calculator of 12. However, there are 3 significant figures in this number and 3 significant figures in this number. Therefore, there should be 3 significant figures in our answer. So our answer is 12.0 grams. The next example. An unknown liquid has a density of 1.32 grams per milliliter. What is the volume of a 14.7 gram sample of the liquid? So again, we have density equals mass over volume. We are given the density and the mass. So 1.32 grams per milliliter equals 14.7 grams divided by an unknown volume. To solve for volume, we would multiply both sides of this equation by volume, and then divide both sides by our 1.32 grams per milliliter. So our answer, volume, equals 14.7 divided by 1.32. Our volume in milliliters in our calculator is 11.13636364. Right? Correct number of significant figures, you have 3 sig figs and 3 sig figs. So you should have 3 in your answer. Therefore, the correctly rounded answer is 11.1 milliliters. Specific gravity is the relationship between the density of a substance and the density of water. In order to calculate this, we divide the density of the sample by the density of water, which is 1 gram per milliliter. It is a unitless quality, since the density of any substance is also, or can also be measured in grams per milliliter. A substance with a specific gravity of 1 has the same numerical value as the density of water. This concludes Chapter 2, Part 2. Thank you for listening.